Okay. Hello, everybody. Wishing you the best and a good, nice day. So, we continue discussing examples related to edge detections. In the previous lecture, I have discussed with you three interesting examples, and now I shall try to explain to you more and more so that you can understand different techniques and methods of analysis the images in order to be able to carry out the required measurements and decisions. So this is another example which is called draw external edges using IMAQ mask region of interest. The block diagram, as you see here, includes IMAQ cast image. This is used to guarantee at the output here a grayscale image. And this grayscale image now is thresholded by using IMAQ threshold function. And as you see, the IMAQ threshold function requires to define the interval or the range of threshold, which is, as you see here, a cluster with two variables. Moreover, we have an additional function called IMAQ mask and IMAQ mask to region of interest function, which we used yesterday. Also, we use IMAQ overlay region of interest and IMAQ inverse function. So really, a number of different virtual instruments, different functions exist here in this example. And it gives you directly the contour or the output edge of the given input or image, which is, as usual, read from a file. So this is the file path. Here it is. And we read this file and get the output image here. This is the image which we get. And this image now is input to the IMAQ cast image 2 to guarantee at the output a grayscale type image here. This is a grayscale type image, which is the input of the IMAQ threshold. So this function receives grayscale and converts the image from grayscale to black and white or binary. And the output, as you see, gives image 2. This is the binary output as a result of IMAQ threshold. Here it is. This is the binary. this is the image, and the black shows the background of the image. Now, this binary image is fed to the image mask and to the as also as a source to the same function here. The output of this function will be fed to IMAQ mask to region of interest. It gives us the output, the descriptor, as you see, which is a cluster here. And this descriptor is the input to IMAQ overlay, which overlays the descriptor output coordinates on the grayscale, sorry, on the binary image itself. The output here is input again to an inverse, IMAQ inverse function to get the final image. So it needs from the listener here just to know each of these functions and how it works and nothing more. Here you do not need to give values of variables except the range of threshold. Here we use between 80 to 240, the lower level, the upper level. And also we give the number, the maximum number of vectors in region of interest. It is normally about 700, sorry, 1,000, about 1,000, 2,000. You give the most appropriate value here and nothing more. So these functions here, all of them are IMAQ create function, which are used to guarantee a buffer space in order to display image 3 and to display image 2 and to display the image, the initial image. So if we go to the block diagram, sorry, if you go to the front panel here, this is the basic initial image which we receive from the file. And this here is the grayscale, sorry, the black and white or the binary image, as you see with the black background. And here is the edge, which is extracted at the output of the inverse function. Yeah. Really, there is nothing here required from the reader except to go to the literature and to understand exactly what the function IMAQ mask does, and IMAQ mask to region of interest converter, and IMAQ overlay region of interest. Concerning the thresholding function, you know this function and you may not need more information about it. Well, if I run it with the constants or the range of threshold given here, you see this doesn't change exactly as, it requires again to go to acquire the address here or the file. It is in the pictures as seen here. Here is the image. So I click it again and I run the function. It will appear again here with the binary image and the edge extracted at the output of the inverse function. If we change, as I suggested to you, the threshold range to become between 140 and 240, for example, here, 140, and down it is the same value, 240, and we run the program, we can see that practically there is no difference. It is working nice and it's okay. If we give another value, suppose that I want to test the program and I want the range to become larger. Suppose this is not 100. No, to become closer, then I want to increase it. 180, for example. 180. This is the lower, and the upper is 240. And if I run, as you see, the edge is not emphasized with the same contrast, different contrast here, but exactly also we achieve a contour or an edge of the image extracted at the output of the inverse function. Okay, we do not need to carry out more investigations in this example. The next example, edge detection using Canny filter. C-A-N-N-Y. It is a name of a scientist. So, as you see, this is the original image which we have. And this is the image which we got at the output of Canny edge detector. But to work with Canny edge detector, we need to variate the filter parameters in order to get maybe more appropriate edge images. So if we go to this block diagram, we find that it is indeed not that complicated. And we read this image from a file, and the address is given here. And here is the image. Now this image is fed as input to as an image source to Canny edge detector or filter. Canny edge detector. Also, we guarantee here a memory space for the image, thresholded image. And here we need maybe to variate the filter parameters, which are shown here. These are the filter parameters which we can vary. This is the image, and this is the Canny filter output or edge detector output. Well, I did really many investigations, and I found interesting to show you this combination of values to give you sigma equal to 4, the high threshold level 0.95, and the lower thresholding level 0.65. Let us put them and have a look. This is 4. This is 0.95. And this is 0.65. The window side is kept 9, and reminding you, normally it should be odd number, not even number. And now if we run the program with the new parameters, we get this image as you see. This is the edges here are emphasized more clearly, ignoring the inner leaves and inner edges of the original image here. Of course, you can variate these values, change them to get another thresholded image as the output, where you get the edges upon request as desired, I mean. Okay, so I think, as you see, these examples are not that complicated and do not require long investigations. The next one is edge detection with Sobel. Sobel also is the name of a scientist. And normally it is used for edge detection, especially when the contrast is not very appropriate. So if we go to the block diagram, we see that there is a file path which is read by the read function, and the output here is fed to IMAQ edge detection. Here you select, you right-click it, and have a constant. This is the constant. Now it is already selected to Sobel, of course, but I can open it, and you can select any of these different models, which give also different quality edge detection. And here, as you see, important to note that the image which we read, it is this image and the input, really. This image, as you see, is shown through an IMAQ copy function. It is not taken directly and shown directly, but through an IMAQ image. This is because when working with Sobel function and many other formological operations, they affect the original image and it could be distorted. So if you want to keep it not distorted, you can do that by using IMAQ copy, and then from the copy, you get the image. So now we are here. We have selected Sobel and included all the code as you see in a while loop for continuous work, and the output is going to be shown here. This is the output. The input is selected as a grayscale picture. This is the grayscale picture. And as you see, the location of it is shown here. And here, this input, the slide, is used to variate the values upon request and not more, in order to change the quality as you see, it is not running. When I run it, you can feel the effect of changing. You see, now it becomes worse, of course, not emphasized. And now also in this range, it is vanishing and distorted. So it seems to be the best value we achieve as a contour or as an edge detector is about this range, about 41. You see, we have the contour or the edge of this cover, for example, here. We have also this rose, as you see, the contour of it or the edge, and all the other components are shown normally and seen clearly. Okay, so we stop it and move to another example. Finding edges. Well, I don't, short name, good name. So what is there in this finding edges example? I told you that IMAQ has worked out a very comprehensive and very accurate tools by using the rakes, horizontal rakes, and by using the spokes in order to define exactly the lengths and some variables through edge detection. So this is an example here where we use a function worked out by IMAQ, which is called IMAQ Clamp Horizontal Maximum. So it means find the maximum value, which is of the object, of course, the maximum length, for example, horizontally, which is at the parallel to the horizontal axis. This function is given here. Let me drag it up. If you go to here, measure distances, double click it, you will find several functions, and one of them, this is the first one, IMAQ Clamp Horizontal Maximum, and it shows to you that if the blue piece here represents the object, you need to find the maximum length by of the coordinates by the horizontal axis. Of course, you can find the minimum and you can find the maximum by the vertical axis or the minimum by the vertical axis. This is our choice, this function, which is shown here. But before working with this function, as you see, it is fed with the image, which is somehow worked out and processed. At the same beginning, we import the image from a file and read it, and this is the image which we get as the output. This is the image which is the car. This is the input image. And we want to measure the distance horizontally and find the maximum the maximum distance between the sides of this machine. So, as I told you, this function carries out this job by using rakes. This is the horizontal rakes for that. The image which we are using is colored machine. So it is described, or its type is U32. We cannot work out this image without converting it to a grayscale level. So the output image, this is the image, is input to extract single color plane function. Extract single color plane function. This, if we go to images, maybe color utilities, and here you find extract color plane. This function which we are working with here. At the output, we get a grayscale image. Here, we will have now a grayscale image. We have converted the colored image to a grayscale image. And this grayscale image is input to IMAQ convolute filter. IMAQ convolute filter also is found here. You go to the filters. No, this is not the filters, it seems to me. This is the files. So let us go to morphology. Back, image processing, morphology. Maybe it is here. No, it is not here. So we go back to processing. IMAQ convolute. No, it must be with the filters. So here the filters, here it is. IMAQ convolute function. This function here is utilized. It requires you to input the image from the left side, and also requires here to connect a kernel, which is a matrix for smoothing, some kind of filter for smoothing the image at the output here. Here it is. It is shown as two-dimensional array, 3 by 3 size. The size of it is 3 by 3 elements. And we have now to find the output, which is the distance, the output of this function. And if we need, we can have also information about edge coordinates, which means the coordinates of the pixels which exist on the edges. They are found here, X and Y, for example, for the first value, X and Y for the second pixel value, and so on. Okay, now what is left? Left here, as you see, this input required for the clamp horizontal maximum. which is a cluster. And this cluster, as you see, must include 4 values which represent the corners of the region of interest here. So I have to draw a rectangle which includes inside it the image, and the program will approximate it and find these are the rakes, parallel rakes, and the function will define the distance, the maximum distance between both sides of the machine. Here is one of them, this red dot, and the other one is this dot. So this value now is measured and given here as 144.24.24 in pixels. Here the measurement all in pixels. I do not convert the pixels to real values here. Okay. What else? Let me go back to explain to you. So this cluster now, as I showed you, must be filled with the coordinates of this point, the first two, left top, X and Y here, and X and Y here. And these values are utilized by the function in order to carry out the job. This requires you to yourself create a cluster, drag constants and put them, this constant and this constant, you have to drag them and put them in the cluster and create the cluster and include the values required by you, because you can see this when you draw the rectangle, you can know exactly what is the coordinates of this value or any value in the image. Look, if I put it here now, for example, the coordinates are 7 and 9. If I put it exactly on the corner, the coordinates are 15 and 20. If I put it inside, it becomes another value. And wherever you go, the pointer gives you the coordinates. So before putting these coordinates here, I have approximately to know the coordinates of this value, of this point, and the coordinates of this point. But this requires you to establish or to construct the cluster and to drag the variables here to put there your parameters. Another way to do that is what is done here. This is also, as you see, a cluster, and this, let me go back, please. And it is now exploded to the 4 components left, top, right, bottom, and the 5th one is normally not used because we are talking about a rectangle which is not rotated by a given angle. Such a rectangle which is in blue is rotated, but we are not working with it. So anyhow, there is a space kept for the additional variable, the 5th variable. If it is needed, you will give its value. And the outputs from the here from the exploded function, or as we know, it is called unbundle by name. So this unbundle by name gives me the 4 variables and I construct here an array, and this array I convert it to a cluster, and this cluster then I feed it here. Well, I do not find any sense here to do that work. I can do it directly by creating the cluster and connected it with the same function directly. So it seems to me there is no problem. The same thing. Now, if I go here, I have to give values here, this value. $16.20, I can put $16.20, 1, 6, the other ordinate 20, and I come here also and take the ordinates of this point, which is 265 by 164. 265 by 164. These coordinates now are given. The path is not given here. I have to go back and to bring it. So I go to the cars where they are and bring one of them. Here are the pictures. Let me go to the desktop, to Jupyter programs, to tutorial 1, maybe there. This is one of them indeed, but I think I am afraid that the size of the here, I think I took this one. So I fix the address of this car. Now I have the address or the file, I have the coordinates, and I can run the program, and I get the exact answer. For this case, the distance is 242 pixels dot 75. To evaluate it by yourself, we can go to this point here. Look, this dot, red dot, and find its x coordinate. It is 19. And if I go to this point here, it is 263. 263 minus 19, as I remember, it was 19, yes? 18 or 19, the same. 19, for example. So the difference will be 4, 2, 244. Yes, here it is 243, exactly the same distance. So this is the way we work with. Yes, of course, as you see, if I want to work with another image, I have to create another image. Let us do that. For example, let me go and create another image. I mean, import another image. Let us import this image, for example. And now we run the program. If you look at the settings of clamp 1, it is there. Here, the function, and here is the settings. really, you are not going, and you do not need exactly to change these settings. They are very close to the real values. But you may work without showing the search area. This is the search area, you see, or search lines. These are the parallel lines, are the search lines. The edges, which is these two dots, or the results, which are, I told you, this distance. You may not need it, so you can put it off. And when you run the program, you don't see it. And now suppose that I am in this position, and I want newly to define the rectangle which contains the image. So approximately I go from the border here upwards, and I think this is okay. If I move, I think it is normal. Maybe it is here from the, I have gone outside a little bit. Let me try again. Okay. So now when I run the program, I don't see anything except I see the result here. So when I put them on and run the program newly, I will get the rakes, the parallel rakes. I get the search area, and I got the 2 points through which I can find the distance, the maximum distance. I think this is clear for you and doesn't require a lot of work to work with. Yes. And that's it. So the work is done, and we move to another example. Okay, we leave it and go to other example. Example number 8. 8.1, 8.2, 8. I will work with 8.1. So it seems to me that we are doing the same job but differently. Here we are using the same input, the same image, to find the edge, but here we use the dilate and erode functions. And we find the output of the dilate function and the output of the erode function and subtract them from each other, feed the difference to IMAQ inverse, and we now can get easily and directly the edge of the given image. So again, we need to go to morphology function set and select there dilate and erode functions. So how to do that? It is not difficult. You remember, we go backwards. Here is the morphology functions. I double click it, I open it. And now here I see IMAQ gray morphology. This, oh, sorry. IMAQ gray morphology, this one. And here I right-click it and select the type of operation I want to do with it. Upwards. And here, in this box, I click the arrow and select dilate, erode, gradient, open, PC close, P close. All these are different functions with somehow different effects on the image. So you need, of course, to go through each of them to read about it, or go to the system here through the help and get information about each of them and the effect of each on the image so that you can use it in a perfect way. According to me, I know that dilate means expanding a little bit the borders of the image. So I selected here the dilate, and the same function which is there upwards here is the function which is downwards here. I also selected here the erode function. And now what happened? Here is the file path to the file, read function, and now I have read the image. The image now I feed it to the erode function, and also I feed it to the dilate function. And at the output, I will get now another image here, somehow, and here I get another image. I subtract the erode one from the dilate one. I will get the difference here, which will be fed to IMAQ inverse, and directly I will get the border of the image. The difference here function is not the difference function which is in a numeric palette. Here is the subtract or difference function. This is different. This is not an IMAQ function. This is a LabVIEW function. If you want to work with the difference function and add and logic functions with IMAQ, you have to go through the IMAQ and go to operators palette. As you see here, this is the operators palette, and you double click it, and here you also will find IMAQ add, IMAQ subtract. This subtract is used here by me. Of course, also IMAQ divide, IMAQ multiply, and also there is logic functions, IMAQ and IMAQ OR, and what else also, XOR, and so on. Anyhow, so as I told you also, of course, I cannot make you remember all of them and know each of them. This comes through practice and willingness of to know more in more depth. Anyhow, the subtract function is, as you see here, used, and its output, as I told you, is fed to IMAQ inverse, and we will get the border or the edges of the function as we achieved in the previous example. So if I go to the block, to the front panel here, here is the file path. I run it, and I get exactly the, as you see, borders of it, the edges of the function. Okay. To be sure also, let us try another function, sorry, another image, which we can find in grayscale. It should be a grayscale image. I think this, Lena, I have converted it one day to a grayscale image. But here it is 16-bit. It seems to me that it will make, maybe it makes problems. Let us try. No, yes, there is a problem. Invalid image type. It should be 8-bit. So I go back and seek for another grayscale image. Suppose this circle template. Now, when I run the program, here is the original image. Here is the circle. And here is the borders of the circle extracted from here, which shows that the program works normally when you subtract the erode function output from the dilate function output. I don't know if we have more examples of this kind. I mean, grayscale. This is a grayscale image here also. Let us try it. As you see, this is the real, and this is the edges shown of different components of the, as you see, in the picture. Okay, so we go out, file, exit, don't save, and we go out to another example, example A2. What do we have here? Okay. This is our block diagram. As you see here, we have used the subtract function, IMAQ subtract. But we subtracted the image from the dilate, the output of the dilate function. This is the output. This is the dilate function, which is fed by the image itself. And now I subtract the image from the dilate output of the image. It gives you also the output edges. What is left here in the picture is how you create the image. This image is not a standard image. I have demonstrated how you can create it. For example, here, using this is IMAQ draw function. This is also IMAQ draw function. This is an if you go up, I think it is here. Maybe here you can find it. IMAQ window. No, not window. It should be at the manipulation here, maybe. IMAQ shift. IMAQ rotate, IMAQ expand. Somewhere very near to this palette, it should be IMAQ draw function. Of course, if you are put in a situation and you cannot find it, you have two ways to manage that. You can go here and make search IMAQ draw. And you will see here, oh, it is out. Again, IMAQ draw. Let us look. Draw area, draw hill, IMAQ draw. Click it and put it here. And the work is done. You are not supposed to go this way always. You can manage also from here. And also, if you have the function as this one here, and you do not know about it, or you need to fix to which palette it belongs, also you can go through the help, and there they will tell you here, owing palette is pixel manipulation. So you have to go to pixel manipulation, and there you will find this function. Okay, so now we use IMAQ draw twice here. The first time, of course, for it to work, at first I have located, this is the IMAQ create. IMAQ create. I have located a buffer area for the image which I'm going to create here. This is, which guarantees that. I have decided the width and height of the image, for example, between 300 and 400 pixels, X and Y. So the X resolution is equal, this is Y resolution, this is X resolution. And now I have a picture ample for these pixels. I want the picture to be filled. This is IMAQ fill image. So I give the image, and at the output, I will get it filled. And now this will be input to our IMAQ draw. Here I decide what to draw. I want to draw the coordinate of a square. For example, this square, 150, 200, 150. I mean, these corners here. I also have drawn another rectangle with these coordinates. Now, both of them are accumulated, they are in series, and give me this shape. I want to extract the contour or the edge of this figure or shape. So what I do, I took this image at the output, here the image, I took it and subtracted it from the dilate function output. And I get at the output the contour as you see here. Now, if we run the program, it will run perfectly. Of course, we can change the image. Instead of having the image from here, we can open this. Let me go. Well, for example, I can go to from the same beginning to create, or from here directly. I can have a copy of the IMAQ create. I can read to the files. I can read IMAQ read an image. I can define the type of the image. And now I can define the file path where I can seek for the image. And now I shall have the image here. I go to the front panel and create a location for display. Then I go back to the block diagram and connect this terminal with this here. And now I have to define the image, but the image, as you see, the address is here. I double click it and go and seek for an example. I want to find another grayscale image here. There in the pictures, I don't have that much of them. Let us take this one, which we have worked with before. Alia battery, for example. And now when I run the program, here it is. Suppose I have it like this. Now I want backwards. I want to make a copy of this function, dilate function, to take the image to the input. And now I have to select that I want to make dilate function. And then at the output here now, I should have a subtraction. And this dilate output will subtract the input. This is source B. The output here now will be the new image. So maybe, okay, let us keep this one here. I can make a copy here and connect it directly with it here. When I go back here, I find two of them. Now, if I run, I shall have a contour. I have it, but it is not clear. So let me say I want to read it by the rainbow. I have the contour here, the contour here, and the contour here. Not exactly, but it works somehow. It needs, now it is more clear, but really, as you see, the work is not that difficult or that complex. You can do it very quickly upon request. As you know, you have to remember only the principle. I should go out of the program and keep it as it is, don't save. And now I can come back to it as it was before, so that not to deteriorate or to distort the image which was created previously. So we are here again. If we go back to our program to summarize it for you, so all what you need is to have the image. Either you create the required image on your own with the shape you want, and then you use the dilate morphological function, and the output of the dilate, you subtract it, the image from the dilate, and then you will get the border directly, which is also a good practice. So as you see, we have many ways to manipulate and many ways really to work with morphological functions, which is good, I think, but it requires, of course, to know all these different methods or different techniques, and to be able to select the one which is the most appropriate for you. Okay, I think today it's enough. In the next lecture, we have about 5 or 6 other examples. I will discuss it with you. Until then, I wish you the best and goodbye.